It's on the summit of Mauna Kea, a dormant volcano on the Big Island of Hawaii. Golden light bathes the huge domes anchoring each end of a narrow white building. A halo of orange, pink, and magenta swirls overhead, while below, waves of clouds form a blanket so thick and wide that it looks like an ocean. The weather on the shore is hot and humid. But here at almost 14,000 feet above sea level, temperatures rapidly drop below 20 degrees Fahrenheit, even in the summer. No trees or plants grow on the rounded hills. Coffee-colored lava and gray cinder cover the mountaintop and crunch underfoot as workers arrive. Except for the occasional howl of the wind, all is silent. When the sky begins to darken, a loud buzzer warns any technicians walking on the decks and catwalks inside the domes. A motor drones as the top and bottom shutters of one of the domes open. The dome rotates, rumbling like a train as its steel wheels roll along a track at the base. One of the twin telescopes at the W.M. Keck Observatory points to the stars. The night's viewing is about to begin. Farther down the mountain, about 2,000 feet above sea level, lies the W.M. Keck Observatory headquarters. From there, astronomers can operate the telescope, using a real-time video connection between headquarters and the observatory. Tonight, Dr. Jeffrey W. Marcy, an astronomer who hunts for planets, is at headquarters. Jason McElroy, an observing assistant, mans the telescope on the summit. Mist hides the sky from headquarters, but Jeff Marcy isn't worried. He studies a computer screen that details the weather conditions at the summit. "Wow, the viewing is excellent, Jason," Marcy says into a microphone. Gentle hills, in the background at right, dot the remote summit of Mauna Kea. They are known as Pu'u in Hawaiian. The Keck 1 telescope peers through the dome opening into the starry night. The Keck 1 and Keck 2 telescopes are the largest twin optical telescopes in the world. Marcy uses the Keck 1. Astronomers like Marcy no longer look directly through a telescope eyepiece. Instead, a device similar to a digital camera records the image in the telescope. The image is transmitted to computers for analysis. The time is almost 7 p.m., the beginning of Marcy's block of time to use the telescope. A long night of planet hunting stretches ahead. He will finish at 5:30 in the morning. For the next 3 days, Marcy will sleep during the day, play tennis late in the afternoon, eat a quick dinner, and then go to the telescope control room at 7 p.m. He keeps his fingers crossed that the good weather will hold. Telescope time is costly, and the instrument is sensitive. When the weather is bad, the telescope shuts down for the night. Tonight, Marcy is excited. Maybe he will find another distant planet orbiting a star like our sun. Maybe this time the planet will be similar to Earth, the kind of planet most likely to sustain life. Since 1995, Marcy, Dr. Paul Butler, and their co-workers have discovered or helped to discover many planets found outside our solar system, which are known as extrasolar planets. Dr. Deborah Fisher, a key member of the team, helps analyze the collected data. As the team develops more and more precise search techniques, Marcy comes closer to his dream of finding a small, rocky, Earth-like planet, one that might harbor life. In 2006, the team announced one of the smallest planets discovered so far. This planet, which orbits the star Gliese 876, is about 6 times more massive than Earth. The planet might seem large, but most of the known extrasolar planets are even bigger. They are about 300 times more massive than Earth, which puts them in a class with Jupiter and Saturn. More recent discoveries have been equally thrilling. In 2007, for the first time, Astronomers determined the composition of an extrasolar planet by figuring out the planet's density. This planet, which orbits the star Gliese 436, is made of rock and water, similar to our Earth. Later that year, Marcy's team announced their finding of a fifth planet orbiting the star 55 Cancri. This artist's interpretation of a planet forming around a distant star looks like Saturn might have looked when it formed in our own solar system. Jason McElroy operates the telescope at the summit. McElroy and Marcy can see each other by video as they work. Marcy is shown in the monitor above McElroy's desk. The first time 5 extrasolar planets have been discovered orbiting one star. As of this writing, the structure of this planetary system is the closest we know of to our own solar system. And new planetary systems are being discovered all the time, by Marcy's team and by others. Is the Earth a 1 in 1,000 shot, a 1 in a million shot? Marcy wonders. He adjusts the controls on one of the 14 computers that line the wall of the telescope control room. Surely in this huge universe there are other planets that have conditions ripe for life. But are there 10 in the Milky Way galaxy, a billion? Or is there only one, our Earth? And if there's a planet like Earth, how likely is it to have intelligent life? Stars and planets are continually forming in the universe. Marcy estimates that one of the 200 billion stars in our Milky Way galaxy, about 10% or 20 billion, have planetary systems. About 1/4, or 5 billion, of these planetary systems probably have a rocky planet like Earth, ripe for life. That means there could be billions of Earth-like planets in our galaxy. Let's suppose, conservatively, that intelligent species live on only one Earth-like planet in a million. According to Marcy, the Milky Way then would have thousands of advanced civilizations. Questions like these spurred Marcy to begin hunting for planets in 1985. At the time, some scientists thought other planets might lie outside our solar system, but no one had ever found one. Marcy wanted evidence. With Butler's help, Marcy refined and adapted a detection method called Doppler spectroscopy. They worked for 10 years to find their first planet. Marcy doesn't detect extrasolar planets while he actually uses the telescope. The discovery occurs much later, after Marcy and his team have charted a star's movement and analyzed the data collected from years of observations. As a scientist, I want to be 100% certain before announcing a new planet, Marcy says. For example, colleagues can say, "How can you be absolutely sure there is a large planet like Jupiter out there?" Well, Jupiter takes 12 years to orbit the Sun. That means we have to chart a Jupiter-like planet for at least 12 years, plus some more, to verify that the planet is repeating its orbit. Despite the challenges of planet hunting, Marcy keeps searching. Ultimately, you have to be passionate and really care about the planets, he says. You are trying to do something that is part of you, as well as something great for the rest of the world. Planet Hunter, Deborah Fisher. Dr. Deborah Fisher analyzed the data that revealed 3 Jupiter-sized planets orbiting the star Upsilon Andromedae. Her examination of star movements was crucial in the discovery of 55 Cancri F, the 5th planet orbiting the star 55 Cancri. Since then, she and her colleague Jeff Valenti have analyzed more than 1,000 stars. They hope to learn more about how planets form. The Upsilon Andromedae system held surprises. The first planet lies so close to the star that it completes an orbit in only 4 days. The second and third planets are about as far from their star as Venus and Mars are from the Sun. I realized at a gut level that the process of forming planets must be easier than scientists had appreciated before, Fisher says. How else could 3 Jupiter-sized planets be crammed into the inner part of the Upsilon Andromedae system? Fisher is also hunting for Earth-like planets around the stars Alpha Centauri A and B, a double star system and our closest neighbor. Says Fisher, if you ever want to travel to another star system, too hard now, this would be a likely destination. Each Keck telescope weighs roughly 300 tons and is as tall as an 8-story building. The primary mirror in each is made up of 36 individual glass hexagons, coated with a thin film of shiny aluminum. Above, the giant lens has been outlined in red. Somewhere in the Milky Way galaxy, a rocky planet similar to Earth may be orbiting a sun-like star. It may even harbor life. In the telescope control room at Keck Observatory's headquarters, Marcy checks the various computer screens. Almost ready to start, Jason, he says into the microphone to McElroy, the technician at the summit. Marcy watches McElroy on the video screen mounted above the computers. Let's take a shot of the sky and see if it's dark enough, Marcy adds. He wants only pure starlight to enter the telescope. Right, McElroy says. In the video screen, he nods. Marcy settles into a swivel chair in front of the 4 main computers. Anyone can have a telescope, he says, but not everyone has a spectrometer. A telescope alone, even one as powerful as the Keck 1, cannot detect a planet outside our solar system. From Earth, a star's light is so bright that it washes out the light from a planet. Think of a searchlight on top of a lighthouse, Marcy explains. If there were a little firefly sitting on that lighthouse, you'd never know. So how does Marcy find a planet if he can't see it? He uses a Doppler spectrometer. If a planet is orbiting a star, the star will wobble as it is pulled by the gravity of the planet. Depending on where the planet lies in its orbit around the star will be tugged either toward the Earth or away from it. In this artist's interpretation, a Jupiter-sized planet is crossing in front of its parent star. So far, most of the planets detected have been the size of Jupiter or larger. A planet's like a frisky dog being walked by its owner, the star, Marcy says. For a star and its planet, the leash is gravity. You can figure out how large the planet is, its mass, by how much the star wobbles. You can also figure out the planet's speed or velocity. The bigger the planet, the faster the star gets yanked around. A spectrometer reveals a star's wobble by recording the changes in its light waves. Light shining from a star, like all light, travels in waves. All white light, including starlight, is made up of the visible colors of light mixed together. The colors of a rainbow, red, orange, yellow, green, blue, indigo, and violet, are known as the visible spectrum, and they always appear in this order because of the lengths of their waves. The longest visible wavelengths are red. The wavelengths of orange, yellow, and so on become increasingly shorter. Violet has the shortest visible wavelength. When scientists talk about the wavelengths of light, they often refer to the blue end and the red end of the spectrum. Doppler effect. The Doppler effect is named after Christian Doppler, an Austrian physicist. He noticed the change in light waves when a light source, such as a star, moves toward or away from an observer, such as an astronomer on Earth. Sound waves also produce Doppler shifts. Listen carefully the next time you hear an ambulance pass by. The "eeeow" of a siren is shrill as the ambulance zooms closer, and the sound waves are compressed. The pitch lowers as the ambulance passes, and the sound waves are stretched out. Wobbling star, unseen planet. When starlight enters the telescope, the spectrum reveals a shift toward blue or red, depending on whether the star is moving toward Earth, blue, or away from it, red. The blue waves of light are compressed. The red are stretched out. When light waves pass through something transparent, such as glass or water, the light slows down. When the speed decreases, the light bends or refracts. If the light is bent sharply enough, as in a prism, the colors split apart from one another. Red light waves bend the least, followed by orange, then yellow, and so on. Violet light waves bend the most. When the waves bend and the colors split from one another, we see all the colors of the rainbow, or spectrum. In a spectrometer, a device similar to a prism collects starlight through the telescope and separates it into a spectrum. Waves of starlight change depending on whether the star is moving away from or toward Earth. If the star is moving toward Earth, the waves are compressed and shift toward the blue end of the spectrum. Green light may look blue, for example, or orange light might look yellow. When the star moves away, the light waves are stretched out and shift toward the red end of the spectrum. Orange light may turn red, or blue light may look green. These changes in color are called Doppler shifts. Over time, a series of alternating red shifts and blue shifts indicate that a planet is causing a star to wobble. Marcy uses a powerful spectrometer known as the high-resolution Eshel spectrometer, HIRES. It was built by a former member of the team, Dr. Stephen Vogt, an astronomer at the University of California, Santa Cruz. Vogt continually improves and updates the spectrometer. The spectrometer at Keck is housed in a small room with steel walls, located next to the telescope's mirrors. The spectrometer is located to the right of the telescope, in the room with the door. The room is as big as a living room, about 20 by 20 feet, and is sealed to keep out dust and moisture. Planet hunting with a spectrometer. Star, starlight, telescope, iodine gas, spectrometer, spectrum, CCD, computer. Starlight travels through the telescope and passes through a glass cylinder of iodine gas. The light continues through the spectrometer, which separates the light into a spectrum that shows patterns of both the gases around the star and the iodine in the cylinder. The spectrum is photographed by a device similar to a charge-coupled device, CCD, light detector, in a digital camera. A computer then stores and analyzes the image. Deborah Fisher observes a spectrum of starlight in the control room at Lick Observatory. The spectrometer works kind of like a digital camera, Marcy explains. It takes a snapshot of the spectrum of light and records it. Marcy points to a computer screen at the far left. This computer controls the exposure time. It's like the control panel on a camera. Smaller stars, which give off less light, need longer exposure times than larger stars. He points to another screen just to the right. And here's where all the spectrometer data is recorded. I'll take this back with me to the University of California, Berkeley, where we'll analyze it. Marcy flips through a sheaf of papers stapled together. This is his script of the stars he'll observe tonight. I've got the whole night planned out here, scene by scene, he says. Marcy has spent hundreds of hours selecting the stars. Currently, he is interested in about 2,000 of them. Tonight, he will focus on 80 stars that he has been following for years. Although Marcy hunts for all kinds of extrasolar planets, he's most passionate about this group of stars. These are the ones he thinks are most likely to harbor Earth-like planets. Over the next 3 nights, Marcy will page through his script, taking measurements of the same 80 stars. Perhaps, after reviewing the new data, he will pare down his search to even fewer stars for his next visit. Maybe in this special group lies an Earth-like planet, waiting to be discovered. Start of orbit, end of orbit. These spectra of starlight show the small Doppler shifts that occur during one complete orbit of a star. Beyond the Milky Way lie tens of billions of other galaxies, many similar to NGC 1232 above, a large spiral galaxy that contains billions of stars and planets.